Good day. I am E20260. My project investigates the impact of moisture content on combustion efficiency and bunker clogging in biomass-fired boilers and develops a waste heat drying system solution. This is an industry collaborative project with Vidul PLC. In this presentation, I will present the knowledge gaps identified, realistic project plan for completion, progress made to date, and the feasibility analysis conducted. Vidullanka operates a 3.3 megawatt biomass power plant with a 16 ton per hour ISJET traveling rate stoker boiler. The full system uses 40 mm glycidia wood chips mixed with small rice husk particles at a 2:1 ratio. The plant faces three major problems due to moisture. The primary problem is reduced combustion efficiency due to high moisture. The second problem is bunker clogging, which requires manual clearing and causing production downtime. Third, high moisture results in unburned carbon in ash, which creates disposal complications. The research has five clearly defined objectives. First, characterize fuel properties at multiple moisture levels using TGA and bomb calorimetry. Then use this surrender equation to predict efficiency improvements. Second objective is to identify the exact critical moisture threshold where bunker clogging begins. Third, determine drying kinetics from 50 to 120 degrees Celsius. Fourth objective is to perform comprehensive techno-economic evaluation on the selected drying system. And the fifth and the final objective is to use ANSYS Fluent to optimize the dryer design and validate against experimental data. I have conducted a comprehensive literature review. This revealed five critical knowledge gaps spanning combustion efficiency, fuel handling, and drying technology. For combustion efficiency, the surrender equation has been established for single species food combustion, but no published study has evaluated its accuracy for mixed biomass systems. Secondly, published glycidia heating values show a large discrepancy. For fuel handling, there is no published study identifying the critical moisture threshold for bunker clogging in mixed fuel systems. Fourth, the clogging mechanism itself is undocumented in literature. For drying technology, there is no published techno-economic analysis of waste heat dryers for traveling grade stokers. This Gantt chart shows the 28-week project timeline. The project began with the literature review. Samples were originally planned for delivery in week 4 but arrived in week 8, creating a delay. Phase 1 spans weeks 9 through 12. I am currently in week 10 in the process of preparing samples for testing. Next, I will walk you through the methodology involved with each of these 4 phases. The experimental methodology is of 4 phases as previously mentioned. Phase 1 is the full characterization phase using TGA and bomb calorimetry to measure fuel properties at multiple moisture levels and then applying these properties to the surrender equation for efficiency prediction. Phase 2 is the bunker clogging investigation. Here I plan to employ angle of repose testing using a tilting box and Hosner ratio measurements for coarse chips. Phase 3 is the drying kinetics. It uses TGA isothermal testing to identify optimal temperature range for drying and followed by oven validation to obtain page model coefficients. Phase 4 splits into 2 parallel tracks. The CFD track uses ANSYS Fluent with a 2D model. The economic track calculates itemized capex and other economical parameters. During weeks 9 and 10, I completed sample preparation using a rigorous protocol. Samples underwent thermal treatment at 105 degrees Celsius to eliminate mold and establish a dry baseline. In weeks 11, I am conducting TGA proximate analysis. Each 90-minute TGA run follows a 3-stage program yielding moisture, ash, volatile matter, and fixed carbon content on a dry basis. Afterwards, In week 12, I will complete bomb calorimetry to determine higher heating values. Based on the literature review conducted, I made 6 evidence-based design decisions as shown in this table. The packed moving bed waste heat dryer was selected after eliminating 3 alternatives. The page drying model was chosen based on superior performance. The Surendra equation and the 2D axisymmetric CFD approach were all selected based on validated literature precedents. Regarding drying technology selection, the literature review systematically eliminated 3 alternatives. The packed moving bed waste heat dryer emerged as the sole viable option. Considering the feasibility, all required equipment is accessible. Experiments and simulations can be done using the resources available at the faculty. All methodologies are validated in published literature for biomass applications, and access to data and samples has been confirmed by the Vidulanka management. Expected outcomes can be seen across 4 areas. Firstly, efficiency gains from phase 1 validation, reducing moisture to around 35% wet basis predicts significant SFC reduction, resulting in substantial annual fuel cost savings. Secondly, operational reliability from phase 2's critical moisture threshold identification. Thirdly, third expected outcome is technical specifications from phases 3 and 4 deliver optimized packed moving bed dryer design. Fourth outcome is the economic justification that I will be able to provide to support the investment decisions that needs to be made. In conclusion, this research project investigates the impact of moisture content on biomass fuel combustion efficiency and evaluates drying methods. I believe through this research I can give solutions to these problems that I have identified and can transform plant operations. Thank you for your attention.